There's a town in Washington state called Ording, population 8,500, sitting on flat, fertile ground next to a river. That ground isn't soil. It's the remains of a wall of mud and rock that buried a forest alive 500 years ago, and nobody can tell you what caused it or when it's coming back. Walk through Ording today and you'll see a quiet farming town, church steeples, a school, a little downtown with a hardware store and a diner. The land is flat because that's what a catastrophic debris flow leaves behind when it finally runs out of energy and stops. The soil is rich because volcanic sediment makes excellent farmland once it settles. People built here for the same reason people build anywhere flat and fertile near a mountain. Nobody chose this site because it was dangerous. They chose it because, on the surface, it looks like some of the best land in the valley. What they were standing on, without knowing the details, was the flattened, compacted memory of the single largest lahar Mount Rainier has produced in the last 1,000 years. To be clear about what Mount Rainier actually is, it's a stratovolcano rising more than 14,000 feet above the surrounding lowlands, part of the same Cascade volcanic arc that produced Mount St. Helens, less than 100 miles to the south. Its last confirmed large eruptions happened roughly 1,100 and 2,300 years ago, which by almost any ordinary standard makes it a quiet mountain. People ski on it, climb it, hike its wildflower meadows every summer, and for the overwhelming majority of that time, nothing about it feels remotely threatening. That quiet is real. It's also, in a very specific sense, beside the point. A lahar is not lava. It is not ash falling from the sky. It is a fast-moving slurry of rock, mud, ice melt, and debris that behaves less like a landslide and more like wet concrete moving at the highway speed. It can start high on a mountain and travel for tens of kilometers, growing as it goes by picking up trees, boulders, and everything else in its path. In the late summer of 1507, one of these flows came off the western side of Mount Rainier, tore down the Puyallup River Valley, and didn't stop until it had traveled more than 60 kilometers. Along the way, it plowed into a stand of mature Douglas fir, some of the trunks more than 3 meters thick, and it didn't just knock them over. It buried them standing, snapped and flattened under roughly 30 meters of rock and mud. Because the burial happened fast, in total, the wood never rotted. The bark stayed on. 5 centuries later, those trees are still down there, sealed in the ground like a fossil made of yesterday. For most of the last century, nobody could say exactly when this happened. Geologists knew there had been a huge flow. They knew roughly when, somewhere in a window of decades, and they knew its name, the electron mud flow, after the small community it buried. But a decades-wide guess isn't good enough if you're trying to understand what triggers an event like this, because you need to line it up against everything else that was happening in the region at the time. That changed only recently, when a team of researchers, Brian Black, Patrick Pringle, and James Vallance, published a study in the journal Geology that finally pinned the event down to a single year, and even a single season. Their method is worth understanding because the precision is what makes the final answer so unsettling. They started with radiocarbon dating on 7 samples taken from buried, bark-bearing Douglas fir. Radiocarbon alone narrowed the event to somewhere between 1477 and 1522, a window of about 45 years, with very high statistical confidence. That's a solid result by most standards. It is not a solid result if what you actually want is a specific year. So the team went further into tree ring analysis, dendrochronology, using the growth pattern locked into the wood itself. Every tree records its local climate year by year in the width of its rings. A cold, dry year produces a narrow ring. A favorable year produces a wide one. Across a region, trees growing in the same climate zone tend to produce matching patterns, almost like a shared fingerprint stamped into wood at the same time. The researchers sampled 21 trees killed by the electron mud flow and measured 86 separate ring sequences from them, enough to build a confident 475-year composite pattern. Then, they compared that pattern against tree ring records from elsewhere in the Pacific Northwest, live trees, archived samples, old growth chronologies stretching back centuries. The best match came from a Douglas fir chronology on Vancouver Island, hundreds of kilometers to the north. That match was tight enough to state the death year without a margin of error. The trees died in 1507. They found one more detail buried in that final ring. In the outermost layer of growth on the bark-bearing trees, the late wood, the darker, denser material a conifer lays down toward the end of a growing season had only just begun to form. That single detail tells you the season, not just the year. The trees were killed in late summer. That detail matters enormously because it's the piece of evidence that starts ruling out the ordinary explanations. If you already know a large volcanic mountain in the Pacific Northwest just produced a catastrophic debris flow, your first assumption is an eruption. Magma rises, pressure builds, the summit or a flank fails, and superheated material tears into a glacier, producing exactly the kind of violent, fast-moving slurry that buried those trees. If that happened in 1507, it should have left a signature. A layer of volcanic ash somewhere in the regional record in a lake bed, a bog, a soil horizon sitting at the right depth and the right date. Researchers went looking for that layer. It isn't there. No ash deposit anywhere in the region corresponds to a 1507 eruption at Mount Rainier. The second obvious suspect is an earthquake. The Pacific Northwest sits above the Cascadia subduction zone, a fault capable of producing enormous earthquakes, and a large enough quake can absolutely trigger a landslide on a compromised slope. But Cascadia's most recent great earthquake is dated with unusual precision, to the year 1700, thanks to a genuinely remarkable piece of detective work involving tsunami records in Japan, and again, tree rings on this side of the Pacific. 1700 is not 1507. The dates simply don't line up. Cascadia didn't do this either. So the largest lahar this mountain has produced in the last 1,000 years, an event violent enough to bury a mature forest and lay down the literal ground that a town of thousands of people now stands on, has no identified eruption behind it and no identified earthquake behind it. The cause is officially unknown. And that single fact should change the way you think about how this mountain is actually being watched. Mount Rainier is monitored seriously. Seismometers, GPS stations that track ground deformation down to fractions of an inch, infrasound sensors, webcams, an entire scientific apparatus built around one core assumption, that a coming catastrophe will announce itself first. Magma doesn't move silently. It cracks rock as it rises, it deforms the surface, it releases gas. That's the theory of the case for basically every actively monitored volcano on Earth. And it's a good theory. It's just that the most destructive event this particular mountain has actually produced, in the modern geological record, didn't follow that script. Nothing rose. Nothing cracked from below in a way anyone could have caught. Something simply let go. To understand why that's possible without magma being involved at all, you have to go inside the mountain itself, not into its plumbing, but into the rock that makes up its body. Mount Rainier is built from andesite, a strong, dense, structurally competent volcanic rock. That strength is what allows a stratovolcano to stand more than 14,000 feet above the surrounding landscape, at slope angles that would collapse instantly if the rock were any weaker. But for thousands of years, hot, acidic, sulfur-bearing water has been circulating through cracks and pore spaces deep inside that structure. This process is called hydrothermal alteration, and it doesn't blow anything up. It works slowly, chemically, mineral by mineral, converting hard andesite into soft, structurally weak clay. This isn't a theoretical process. A detailed survey published in the Journal of Volcanology and Geothermal Research mapped exactly where this alteration has occurred across the mountain and linked the mapped zones directly to debris flow hazard. Geologists don't have to guess where the mountain has been chemically compromised. They can identify it in hand samples, rock that should ring like stone under a hammer, but instead crumbles pale and soft, because the internal mineral structure has effectively been dissolved and rebuilt as something closer to wet clay. There are two consequences to this transformation, and the second is worse than the first. The first is that altered rock tends to fail catastrophically rather than gradually. A healthy rock slope sheds material continuously, small rock falls relieving stress bit by bit over time. A slope loaded with clay behaves differently. It holds together right up until it doesn't, and then a very large mass moves all at once. The second consequence is what that same clay does after the initial failure. Clay holds water. It doesn't dewater and stop the way a landslide made of clean, dry rock eventually does within a few kilometers of its source. A debris flow loaded with clay stays fluid, keeps its momentum, and can travel for tens of kilometers past the base of the mountain, well beyond where a normal rock slide would have run out of energy. The same chemistry that quietly weakens the mountain's structure is the exact chemistry that gives the resulting flow its terrifying range. In 2001, 3 researchers, Reed, Christensen, and Valance, published a modeling study asking a very specific question: where on this mountain could a large flank collapse actually begin? Their conclusion was unusually precise for a hazard study. A sizable collapse, anything larger than roughly 1/10 of a cubic kilometer, requires 3 conditions to line up in exactly the same location. It needs a large volume of hydrothermally weakened rock. That rock needs to sit high on the mountain's structure, and the slope beneath it needs to be steep. Having any 2 of those conditions in one place is a geology problem. Having all 3 together is closer to a countdown. It's worth sitting with how small that threshold really is. 1/10 of a cubic kilometer sounds like a great deal of rock, and it is, but it's only about 1/4 of the size of the largest collapse this mountain has actually produced in its history. The model isn't describing a worst-case scenario. It's describing the smallest failure that would still count as genuinely dangerous, and then asking where even that minimum event could physically occur. On Mount Rainier, all 3 conditions overlap in exactly one place. It's called the Sunset Amphitheater, a steep headwall region on the upper west flank, above the Tahoma Glacier. Beneath that headwall sits more than 500 meters of water-saturated, hydrothermally altered rock. The United States Geological Survey states this plainly in its own hazard assessments. The greatest risk of a landslide-triggered lahar comes from the west side of the volcano, because the west side holds the largest volume of weakened rock anywhere on the mountain. This isn't a hypothesis waiting to be confirmed. Within roughly the last 100 years, a smaller rock avalanche broke loose from that exact head wall and slid onto the Tahoma Glacier. Researchers examined the debris and found it contained the same magmatic hydrothermal alteration minerals mapped in the broader survey. The weak rock at the top of Mount Rainier's most dangerous sector has already failed once, at small scale, recently enough that the deposit is still sitting there on the ice, visible and identifiable today. If you want to know what a full-scale version of that failure actually looks like, you don't need a computer model. You can look at the ground people are currently building homes and schools on. Roughly 5,600 years ago, the entire summit and northeast flank of Mount Rainier collapsed in one event. The volume was somewhere between 3.5 and 4 cubic kilometers, roughly 40 times the threshold that modern modeling treats as merely sizable. It began as a massive, water-saturated avalanche of already weakened rock and transformed into a lahar as it moved. This event is called the Osceola Mudflow, and its numbers are difficult to hold in your head all at once. It filled the White River Valley to a depth of 80 to 150 meters. It spread across more than 200 square kilometers of the Puget Sound lowlands. It traveled 70 to 100 kilometers from the mountain, reaching the ground now occupied by the city of Tacoma and by Kent, a suburb of Seattle. When it hit Puget Sound, it didn't stop at the shoreline. It kept moving underwater for as much as 20 kilometers further. The Osceola event also physically removed the top of the mountain, leaving behind a horseshoe-shaped crater open to the northeast. The same shape Mount St. Helens left after its own collapse in 1980. Rainier spent the following several thousand years slowly rebuilding a new summit cone inside that old scar. The peak people photograph from Seattle today is younger than the collapse that made room for it, a new structure standing on top of the failure surface of the one before it. Here's the detail that explains why the danger sits exactly where it does today. The Osceola collapse stripped the most intensely altered rock out of the volcano's summit, its east flank and its interior, carrying that material away into Puget Sound. What survived, and what has continued to chemically weaken over the 5,600 years since, is concentrated almost entirely on the upper west flank, in the Sunset Amphitheater. The mountain's most dangerous face today isn't the face it presented before its last great collapse. The danger migrated, and both the mineral mapping and the computer modeling point to the same location. There's a more recent precedent from that exact sector too. Sometime between roughly 2,500 and 2,600 years ago, an event called the Round Pass Mudflow began as a sector collapse of hydrothermally altered rock coming off the Sunset Amphitheater and the Tahoma Glacier headwall. In other words, the only location on the mountain that currently satisfies all three conditions for a large collapse has already produced one before, and whatever eventually comes off that slope will have an enormous amount of water to work with. Mount Rainier holds an almost absurd volume of snow and glacial ice, more than 150 billion cubic feet. Put together, Mount Hood, the Three Sisters, and Mount Shasta, three of the other major volcanoes in the Cascade Range, hold roughly 22.5 billion cubic feet combined. Rainier alone carries close to 7 times as much ice as those three mountains put together. That means any large-scale collapse in Rainier has access to a water supply that no other volcano in the range can match, which is precisely what turns a rock slide into a lahar capable of reaching a city. So what actually stands between that mechanism and the people living downhill? In practice, it comes down to a detection network and a stopwatch. Lahar monitoring at Mount Rainier began in 1995. The first physical detection system went into the Carbon and Puyallup river valleys a few years later. It's been expanded steadily since, new stations added through the late 2010s and into the 2020s, with additional sites planned. The system is run by the Pierce County Department of Emergency Management with technical support from the United States Geological Survey, and it works through arrays of ground sensors placed along the volcano slopes and the valley floors below. It's important to be precise about what this system actually does, because it's often described wrong. It doesn't forecast anything. It can't warn you that a lahar is coming before it starts moving. What it does is detect a lahar that has already begun, the ground vibrations of tens of millions of tons of debris moving at speed, and convert that detection almost instantly into sirens and automated alerts. The entire value of the system lives inside the gap between the moment a sensor trips and the moment the flow physically arrives somewhere people live. Depending on which USGS model and which drainage you look at, that gap has been estimated at anywhere from around 40 minutes to about an hour for a town like Orting, and as little as 5 minutes for communities sitting closer to the park boundary itself. That gap is the entire margin of safety for roughly 90,000 people living inside the mapped hazard zones around this mountain, the highest debris flow exposed population of any volcano in the United States. The Puyallup River Valley, the same drainage the electron mud flow traveled through in 1507, carries the greatest concentrated risk, which is exactly why the communities along it practice constantly. School districts across East Pierce County run lahar evacuation drills on a regular schedule, and Ording itself runs one every year. In 2024, more than 45,000 students across the region took part in what's considered the largest lahar evacuation drill in the world, walking the marked evacuation routes to higher ground on foot, because the road network in that valley would never clear fast enough by car. Another full-scale regional exercise is scheduled for the spring of 2026, testing upgraded detection stations and a warning system that now pushes alerts to 2 separate emergency operations centers around the clock, with sirens that deliver bilingual voice instructions rather than a single generic tone. Those sirens aren't just installed and forgotten. Pierce County tests its full network on the first Monday of every month, a scheduled sound check across dozens of stations strung through the Puyallup and Nisqually valleys, so that the tone is familiar, long before anyone might need to react to it in earnest. Emergency planners have also built out something called the LAHAR Rapid Action Plan, a coordination document used by first responders across every jurisdiction sitting inside the mapped evacuation zone, spelling out who does what in the first minutes after detection, because coordination is the part that tends to fail first in a real emergency, not the technology. The alert level for Mount Rainier is green, and there's no honest reason for it to be anything else right now. But it's worth looking closely at the most recent reminder of what's actually happening underneath that green light. In the summer of 2025, Mount Rainier produced the largest earthquake swarm ever recorded at the volcano, more than 1,350 located earthquakes, with thousands more too small to pinpoint, peaking at dozens of recorded events per hour at the height of the activity. The largest single quake reached a modest magnitude of 4, several kilometers beneath the summit. Nobody on the surface felt any of it. The United States Geological Survey and the Pacific Northwest Seismic Network monitored the swarm closely, watched it decline over the following weeks, and by late August, formally confirmed that seismicity had returned to typical background rates. Their conclusion was that the swarm was consistent with fluid circulation along pre-existing faults deep inside the volcano, the ordinary, if energetic, signature of the mountain's hydrothermal plumbing, rather than any sign of rising magma. The alert level never moved during any of it. That conclusion is almost certainly correct, and it's not a reason for alarm on its own. But it's worth noticing exactly what those words describe. Fluid circulating along pre-existing faults is the hydrothermal system. It is the same slow chemical process that has spent thousands of years quietly converting solid, load-bearing andesite into the soft, saturated clay sitting under the Sunset Amphitheater right now. The largest seismic swarm ever recorded at this mountain wasn't a warning of an eruption. It was, in effect, the sound of the machinery that does the long-term damage, running normally, exactly as it has for millennia, just briefly loud enough for instruments to notice. 519 years have now passed since the electron mudflow buried that forest and laid the ground Ording sits on today. Researchers estimate the recurrence interval for a lahar of that scale, based on roughly 6,000 years of layered deposits around the volcano, at somewhere between 500 and 1,000 years. Don't read that number as a countdown clock, because it isn't one. An average calculated across millennia of geological history doesn't schedule the next event, and 519 years sits comfortably inside that window rather than past it. But the window is real, and so is everything sitting inside it right now. 90,000 people, a detection system with a margin measured in minutes, and a mountain whose most dangerous face is defined not by anything you could see from a distance, but by rock that has already quietly stopped being rock. Researchers studying the electron event have said their next step is to comb through historical temperature and precipitation records from around 1507, looking for conditions that might have made a summer failure more likely. Their leading working idea, based on the late summer timing revealed in the tree rings, is meltwater. Slope failures in the Pacific Northwest are overwhelmingly winter events, driven by weeks of rain soaking already unstable ground. But the electron mudflow happened in late summer, in a season that's usually dry, which quietly eliminates the single most common explanation for a large landslide in this part of the world. What's left is the possibility that unusually heavy snow and ice melt on the upper mountain late in the season, saturated the altered rock inside the Sunset Amphitheater, raised the pressure inside material that was already behaving like wet clay, and reduced the force needed to make that slope let go. Nothing about that mechanism requires magma. It doesn't require an earthquake. It doesn't require a storm. It only requires a warm summer acting on a mountain that has already been quietly rotting from the inside for thousands of years, and that combination is one that this particular mountain can produce again without ever giving the instruments watching it a single clear signal beforehand. There are really only a few things that would change this picture. Deformation monitoring, finally catching that specific head wall in the act of moving, months or years before a failure. A field discovery that finally identifies what actually triggered 1507, a hidden ash layer, a matching earthquake horizon, or evidence of a hydrothermal explosion of the right age, or the completion of the detection network's expansion specifically into the western drainages, which is what will ultimately decide how many of those 40 or 50 minutes are actually usable by the people who need them. Until one of those things happens, the honest summary of Mount Rainier is this: it doesn't need to erupt to kill people. It has already done exactly that once without warning 519 years ago. And the slow chemical process that made that possible is still running today inside a mountain that looks, from every angle anyone can currently monitor, completely calm.